Hello students, in the previous video we have started discussing on basic processor unit and we have discussed up to register transfer. So in this video we will start discussing about the rest of the topics which are all under basic processing unit. To fetch a word from memory, the processor has to specify the address of the memory location where this information is stored and request a read operation. This applies whether the information to be fetched represents an instruction in a program or an operand specified by an instruction. The processor transfers the required address to the memory address register, whose output is being connected to the address lines of the memory bus. At the same time, the processor uses the control line of memory bus to indicate that their read operation is needed. When the requested data are received from the memory, they are stored in register, that is memory data register, from where they can be transferred to other registers in the processor. The connection of register, that is memory data register, is being illustrated here. It has four control signals: MDR in, MDR out control, and the connection, these two controls are being connected to the internal processor bus, and MDR in E and MDR out E are being connected to the external processor bus. The circuit in this figure 7.3 is easily modified to provide the additional connection. A 3-input multiplexer instead of 2-input, a 3-input multiplexer can be used with memory bus data line connected to the third line. So it is being modified as 3-input with memory bus data line connected to the third input. This input is being selected when the MDR in E, this is equal to 1. A second tri-state gate connected to MDR out E can be used to connect the output of flip-flop to the memory bus. So during the memory read and write operation, the timing of internal processor operations must be coordinated with the response of addressed device on the memory bus. The processor completes one internal data transfer in one clock cycle. The speed of operation of the addressed device, on the other hand, varies with the device. So the processor completes one internal data transfer in one clock cycle. The speed of operation of the address device, on the other hand, varies with the device. Typically, a cache will respond to a memory read request in one clock cycle. However, when a cache miss occurs, the request is forwarded to main memory, which introduces a delay of several clock cycles. A read or write request may also be intended for a register in memory mapped I/O device. Such I/O registers are not cached, so their access always takes a number of clock cycles. To To accommodate the variability in response time, the processor waits until it receives an indication that the requested read operation has been completed. We will assume that the control signal called memory function completed, MFC, is used for this purpose. The addressed device sets this signal to 1 to indicate the connection of the specified location which has been read and are available on the data line of the memory bus. As an example of read operation, consider the instruction move R1, R2. So consider this instruction move R1, R2. The action needed to execute these instructions are: first is of the content of register R1 is being moved to memory address register. Then it starts a read operation on the memory bus. Next, it will wait for the memory function complete response from the memory. Then it will load the memory data register from the memory bus. So finally, from the memory data register, the data is being loaded to register R2. So these actions may be carried out as a separate step, but some can be combined into a single step. Each action can be completed in one clock cycle except action 3, which requires one or more clock cycles. That is, action C3 is nothing but of wait for the memory function completed. So except the action 3, which requires one or more clock cycles depending on the speed of the addressed device. For simplicity, Let, let us assume that the output of memory address register is enabled all the times. Thus, the content of memory address register are always available on the address line of the memory bus. This is the case when the processor is the bus master. When a new address is loaded into memory address register, it will appear on the memory bus at the beginning of next clock cycle as shown in this diagram. A read control signal is being activated at the same time as MAR is being loaded. At the same time as the MAR is being loaded. You can see it here. This is the case when the processor is the bus master. So when read is being enabled at the same time MARN is being enabled. So this is the case where the processor is the bus master. When a new address is loaded into the MAR, it will appear on the memory bus at the beginning of the next clock cycle as shown here. So it will be appearing only on the next clock cycle. A read control signal is activated at the same time when the MAR is loaded. This signal will cause the bus interface circuit to send a read command MR on the bus. With this arrangement, we have combined action 1 and 2 into a single control step. That is, action 1 is MAR the content of register R1 is being read from the memory address. This is of step 1, and the action 2 was start a read operation on the memory bus. Read operation on the memory bus. So these two actions are being combined into a single control step. So action 3 and 4 can also be combined by activating control signal MDR in E while waiting for a response from the memory. Thus, the data received from the memory are loaded into MDR at the end of the clock cycle in which the MFC signal is received. So you can see it here. So as MDR in is being activated and MFC is being activated at the end of the clock cycle. So in the next clock cycle, the MDR out is activated to transfer the data to register R2. This means that the memory read operation requires 3 steps which can be described by the signal being activated as follows. That is, first R1 out, MAR in, followed by means of a read. Next, MDR in and WMFC, that is memory fetch wait control. Next, MDR out, and it is being given to the register R2 is being in, where this WMFC is a control signal that causes the processor control circuitry to wait for the arrival of the MFC signal. So it is nothing but of a wait signal which is being used until the MFC signal arrives. So this figure shows the MDR in is equal to 1, is set to 1 for exactly the same period as read command MR. That is, MDR in is being set to 1 as similar to that of the command MR. Hence, in the subsequent discussion, we will not specify the value of MDR in E explicitly, with the understanding that it is always equal to MR. Now, let us discuss about storing a word in memory. Writing a word into memory location follows a similar procedure. The desired address is loaded into the memory address register. Then the data to be written or loaded into MDR and a write command is issued. Hence, executing the instruction move R2, R requires the following sequence. That is, the first step is from MAR in, it is being outed to the R1 register. Then from R2 out, it is being given to memory data register in, then it is being written into it. So from memory data register out E, it is being waited until the fetch instruction is being, fetch control signal is being received. So as in the case of read operation, the write control signal causes the memory bus interface hardware to issue a write command on the memory bus. The processor remains in step 3 until the memory operation is completed and MFC response is being received. So this is of step 1 and this is of step 2 and this is of step 3. I will repeat it. So in this case of read operation, the write control signal causes the memory bus interface hardware to issue a write command signal on the memory bus. The processor remains in step 3 until the memory operation is completed and the MFC response is received. So next we will discuss about the execution of a complete instruction. Let us now put together the sequence of elementary operation required to execute one instruction. Consider the instruction add R3, R1, which adds the content of memory location pointed by R3 to register R1. Executing this instruction requires the following steps. So first it will fetch the instruction. Next, fetch the operand, that is the content of the memory location pointed out by R3. Next, it performs addition. Then it will load the result into R1. So the figure here shows the sequence of control steps required to perform this addition operation for a single bus architecture. The instruction execution proceeds as follows. In step 1, the instruction fetch operation is initiated by loading the content of program counter into the memory address register and sending a read request to the memory. The select signal is set to select 4. which causes the multiplexer to select the constant 4. It will select the constant 4. This value was added to the operand at input B. So this will be added to the operand at input B, which is the content of the program counter, and the result is stored in the register Z. The updated value is moved from register Z back into the PC during step 2. While waiting for the memory to respond. In step 3, the word fetches the fetched in step 3, the word fetched from the memory is loaded into the instruction register. So the step 1 through 3 constitute the instruction fetch phase. So this is nothing but of instruction fetch phase, which is the same for all the instructions. The instruction decoding circuit interrupts the content of instruction register at the beginning of step 4. This enables the control circuitry to activate the control signal for step 4 through step 7, which constitute the execution phase. This is nothing but of the execution phase. The content of register R3 are transferred to the memory address register in step 4, and a memory read operation is initiated. Then the content of R1 are transferred to register Y. That is here. It is being transferred to register Y in step 5 to prepare for the addition operation. Okay. So when the read operation is completed, the memory operand is available in the register memory data register, and the additional operation is being performed in step 6. The content of MDR are gated to the bus and thus also to the B input of ALU, and register Y is being selected as the second input to ALU by choosing select Y. The sum is stored in the register Z. Then it is being transferred to R1 in step 7. So the N signal causes a new instruction fetch cycle to begin by returning to step 1. So this discussion accounts for all control signals in the figure 7.6 except Y in step 2. There is no need to copy the updated content of PC into register Y when executing the add instruction, but in branch instruction the updated value of PC is needed to compute the branch target address. To speed up the execution of the branch instruction, this value was copied to register Y in step 2. Since step 2 is a part of fetch phase, the same action will be performed for all the instructions. This does not cause us any harm because register Y is not used for any other purpose at that time. Next, let us discuss about execution of branch instruction. A branch instruction replaces the content of program counter with the branch target address. This address is usually obtained by adding an offset value X, which is given in the branch instruction to update the value of program counter. The offset X is usually the difference between the branch target address and the address immediately following the branch instruction. So This figure shows the control sequence that implies an unconditional branch instruction. The processing starts as usual with the fetch phase. This phase ends when the instruction is loaded into the instruction register. That is these three steps, as we have already seen, and I have stressed that the first three steps are instruction fetch phase, and this ends when the thing is being loaded into the instruction register in step 3. The offset value is extracted from the instruction register by the instruction decode circuit, which will also perform sign extension if required. Since the value of updated program counter is already available in register Y, the offset X is gated onto the bus in step 4 and an addition operation is performed. The result, which is the branch target address, and it is being loaded into the program counter in step 5. The offset X used in branch instruction is usually the difference between the branch target address and the address immediately following the branch instruction. For example, if the branch instruction is at location 2000, you assume that the branch instruction is at location 2000, and if the branch target address branch instruction is in location 2000 and the branch target is at 2050. So the value of X must be 46. The reason for this can be readily appreciated from the control sequence, as we have discussed, that is the program counter is already incremented by 4, so the program counter will be holding 2004, and when it is added with 46, automatically it jumps to the location 2050. We used the single bus structure to illustrate the basic idea so far. So the resulting control sequence which we have discussed are quite long, because only one data item can be transferred over the bus in a clock cycle. To reduce the number of steps, we need most commercial processor provided with multiple internal paths that enable several transfers to take place in parallel. So the figure shown here depicts a 3-bus structure used to connect the registers and the ALU of a processor. All general purpose registers are combined into a single block called register file. In VLSI technology, the most efficient way to implement a number of registers is in the form of an array of memory cells similar to those used in implementation of random access memory. So the register files shown here is said to have 3 ports. There are 2 output ports allowing the content of 2 different registers to be accessed simultaneously and have their content placed on bus A and B. The third port allows the data on bus C to be loaded into the third register during the same clock cycle. Buses A and B Buses A and B are used to transfer the source operand to A and B input to the ALU, where an arithmetic or logic operation can be performed. The result is transferred to the destination over bus C. If needed, the ALU may simply pass one of its two input operands unmodified to bus C. We will call the ALU control signal for such an operand as R is equal to A or R is equal to B. The three bus arrangements obviates the need for register Y and Z in the previous figure what we have discussed. A second feature in this figure is the introduction of the incremental unit, which is used to increment the program counter by 4. Using the incrementer eliminates the need to add 4 to the program counter using the main ALU as shown in the previous single bus architecture. The source for the constant 4 at the ALU input multiplexer is still useful. It can be used to increment other addresses such as memory address in load multiply and store multiply instructions. So consider a 3 operand instruction as shown here. The control sequence for executing this instruction is being given here in step 1. So in step 1, the content of program counter are passed to the ALU. The content of program counter are passed to the ALU using R is equal to B control signal, right? Using this control signal and loaded into MAR to start a memory read operation. To start a memory read operation. At the same time, the program counter is incremented by 4. Note, the value loaded into MAR is the original content of the program counter. The incremented value is loaded into program counter at the end of the clock cycle and will not affect the content of MAR. So in step 2, the processor waits for MFC and loads the data received into MDR. So it waits for MFC, waits for MFC and load the data into MDR. In step 2, the processor waits for MFC and loads the data received into MDR. Then transfers them to the instruction register in step 3. Finally, the execution phase of the instruction requires only one control step to complete the step 4. By providing more paths for data transfer, a significant reduction in the number of clock cycles needed to execute an instruction is achieved. So an exercise is being given, that is, what is the control sequence for the execution of instruction add R1, R2, including the instruction fetch phase. So assume a single bus architecture and complete this exercise and try to upload it in Moodle. So the next topic for our discussion is hardwire control. To execute instructions, the processor must have some mean of generating the control signal needed in the processor sequence. Computer designers uses a wide variety of techniques to solve this problem. The approach used fall into one of two categories. One is of hardwire control and other is of microprogrammed control. We discuss each of these techniques in detail, starting with hardware control now, and the microprogram control was already discussed in the class. Hope you remember it. So considering the sequence of the control signal, we are going to see a diagram now. So in this figure or diagram, each state or count of this counter corresponds to one control step. The required control signals are determined by the following informations: the content of the control step counter, the content of instruction register, the content of conditional code flag, and external input signals such as MFC and interrupt request. To gain insight into the structure of the control unit, we start with a simplified view of the hardware involved. The decoder and encoder block is a combinational circuit that generates the required control output depending on the state of all its inputs. By separating the decoding and encoding function, we obtain the more detailed block diagram. The step decoder, by separating the decoding and encoding function, we obtain a clear insight of this particular detailed block diagram. The step decoder provides a separate signal line for each step or time slot in control sequence. Similarly, the output of instruction decoder in the instruction register, one of the output line INS1 through INSM is set to 1 and all other lines are set to 0. The input signal to encoder block are combined to generate the individual control signals Y in, PC out, add, end, and so on. An example of how the encoder generates the ZN control signal for the processor organization is shown now. An example of how the encoder generates the Z-in control signal for the processor organization is shown here. Right? So this circuit implements the logical function Zn is equal to T1 plus T6 and plus T4 VR plus so on. This signal is asserted during the time slot T1 for all instructions, during T6 for an add instruction, and T4 for an unconditional branch instruction, and so on. The logical function for Zn is derived from the control sequence in the figure 7.6 and 7.7, which we have already discussed. So this figure shows the circuit that generates the n control signal for the logic function n. The n signal starts a new instruction fetch cycle by resetting the control step counter to its starting value. So the control hardware shown previously can be viewed as a state machine that changes from one state to another in every clock cycle depending on the content of the instruction register, the condition code, and the external input. The output of state machine are the control signals. The sequence of operations carried out by this machine is determined by writing of the logical element, hence the name hardwire. A controller that uses this approach can operate at high speed. However, it has little flexibility and the complexity of the instruction set is it can implement is limited. Now let us see a complete processor. A complete processor can be designed using the structure as shown in the figure. This structure has an instruction unit that fetches instruction from an instruction cache or from the main memory when the desired instructions are not already in the cache. It has a separate processing unit to deal with integer data and floating point data. Each of these units can be organized. A data cache is inserted between these units and the main memory. Using separate caches for instruction and data is a common practice in many processors today. Other processors use a single cache that stores both instruction and data. The processor is connected to the system bus and hence to set the rest of the computer by means of the bus interface. Although we have shown just one integer and one floating point unit in this particular block diagram, a processor may include several units of each types to increase the potential for concurrent operations. The way in which the multiple units can be organized to increase the rate of instruction execution is being discussed in the pipelining, which we have already discussed in the class.